Hello everyone, I'm glad to present our work Ethane, an asymmetric file system for disaggregated persistent memory. Our presentation includes 4 parts. First, we would like to introduce the background and the motivation of our work. Then we describe the Ethane's detailed design and implementation. We show the evaluation results in the third part. Finally, we give a conclusion. Today's data center face serious performance issues. With current memory and storage devices, it is easy to achieve nanoseconds or milliseconds of request latency for data center services. However, achieving microsecond scale service is extremely hard. On the one side, SSDs or HDDs is too slow to achieve this performance goal. On the other side, although DRAM is very fast, however, its high prices limits its widely usage. Microsecond scale services such as online shopping, e-commerce, and online gaming are prevalent in our daily life. It is important to guarantee their service qualities. Fortunately, emerging hardware like ultra-fast persistent memory and low-latency RDMA technologies open up an opportunity to overcome this challenge. Persistent memory like 3D export is commercialized today. Those persistent memory devices offer hundreds of nanoseconds latency, high storage density, and large bandwidth. In addition, a series of data connectivity technologies such as Metro RDMA, NVIDIA NVLink, and forthcoming CXL enable transparent and low latency memory expansion. Existing distributed file systems extensively use those high-speed hardware. Each file system node incorporates a number of persistent memory devices and connected with RDMA network. This file system architecture, termed the symmetric PM file system, has 3 performance and cost issues. First, file system data are scattered over a cluster of loads. As a result, when serving a client request, the server load has to interact with multiple other loads, resulting in expensive network round trips. For example, we measure the end-to-end request latency of CIFS. It shows a request has to pass through multiple storage layers to complete the request. The load interaction takes 162 microseconds and occupy around 60% of the total execution time. When distributed data meets non-uniform access patterns, the load imbalance problem arises. As a single node only can be equipped with a small number of PM devices, the server node storing the hot file becomes a performance bottleneck, crippling the overall system performance. To remedy the bottleneck, the node administrators have to purchase more machines. Unfortunately, besides the necessary PM devices, additional expenses has to be paid for encapsulated processors and other devices. It significantly increases the total cost of ownership for data center vendors. Take the Hadoop as an example. Both map and reduce phase in Hadoop has 2 phases. If the L phases require more storage devices, the administrator adds more machines. However, those machines are over-provisioned for the computing phase, wasting hardware resources. To summarize, this hardware usage magnifies PM's drawbacks of limited capacity and high price and underutilized precious PM resources. Our paper finds that expensive cross-node interaction, weak single-node capability, and costly scale-out performance result in unpredictable request latency, degraded overall performance, and high monetary costs for current distributed file systems. Decoupling PMs from monolithic machines and aggregating them in a dedicated memory pool is a promising solution. The disaggregated PM architecture enables efficient and cost-effective PM sharing with fast data access. Either a CN or a MN is a specialized machine that assembles blades of computing or memory resources. It exhibits much stronger hardware capability than a monolithic machine in the asymmetric PM architecture. Moreover, the shared PM pool embraces the fast involved data connectivity technology like RDMA and CXL. It supports low-latency data connections with high aggregated bandwidth. Finally, the DPM allows independent scaling of two types of hardware resources. The administrator could provision or deprovision a specific type of hardware resource flexibly and on demand. This novel hardware architecture achieves high resource elasticity, strong fault isolation, and high resource utilization at the same time. To drive the DPM system, we deployment the compound file system architecture with a key insight. The DPM features imbalanced computing and memory resource provision between CNs and MNs. A CN is equipped with a powerful processing unit and limited memory capacity. In contrast, MNs manages a large memory pool consisting of tens or even hundreds of PM modules. However, every MN is only equipped with weak computing units and that support running necessary system tasks. This characteristic inspires us to design an asymmetric file system architecture, which splits file system functionality into a control plane FS and a data plane FS, making the best use of hardware resources. Next, we would describe the proposed file system architecture in detail. This asymmetric file system architecture separates FS object manipulation from storage. The CNs exhibit superior computing capability. We design a set of cache FSs for the control plane FS that run atop available CNs. Each cache FS instance maintains a cached partial view in its local small DRAM. On the other side, MNs provide a shared memory pool with PB-scale PM modules connected through high-performance NICs. Because the MN offers a global view of the whole file system, we define the data plane FS as a shared FS, which shares data over disjoint PM modules and parallelizes data access paths with hardware-provided parallelism. We would present cache plane FS design here. The cache FS mainly consists of a namespace cache and a block cache. It communicates with backend shared FS with shared logs. This figure shows a system called procedure in Ethane. A syscall has an operation log, OP log, which includes a data log, D log, and a meta log, M log. In the first step, the cache FS creates a D log and a M log for a syscall. It first writes the D log in the private log region via RDMA write. Then it uses another RDMA read in order to flash the MN's PCIe buffer and process the D log. Persisting the D log ensures the data durability of the syscall, leveraging the in-order delivery property provided by the commodity NICs. We issue those two RDMA requests simultaneously. In the second step, the cache FS writes the M log in the global log order array. The M log order in the order array reflects the order of corresponding syscall executions. A naive solution is using RDMA CAS to append M logs into a list one by one. However, it causes high NIC contention. We propose the log arena mechanism to reduce log append contention. Our insight is that producing a sequence of M logs for non-reusable syscalls does not require non-reusable M log append. An arena consists of a number of slots for storing M logs. An arena insertion consists of two steps, an M log insert and filling preceding empty slots. In step 1, every cache FS randomly picks up an empty slot in the current arena and uses an RDMA CAS to insert the M log. This randomization policy efficiently avoids the contention during the M log insert. When a cache FS finishes the arena insertion, it should ensure that there are no empty slots preceding the inserted M log. To this end, it scans preceding slots and inserts insert pseudo mlogs if there are empty slots so as to complement the log history. That pseudo mlogs may cause another concurrent cache FS false. For example, T1 in this figure, it would reinsert the mlog. In the third step, we play back logs and then perform the final syscall. We reduce the log playback latency with two technicals. We propose file lineage-based dependency check to reduce the number of playback logs. We validate the dependency of two file system operation based on file lineage. This figure shows three different file lineages. The second technical reuses the playback results of previous playback routines. This diagram shows the log playback procedure. For file path, we calculate its file lineage and query the skip table to determine the start and the end position of this log playback. Then we read those mlogs one by one and check their dependency. Finally, if this mlog has been replayed before, we can directly use the result. Otherwise, we perform a full log replay. The data plane FS provides a shared DPM-friendly storage layer. First, it provides a KV-based storage paradigm to unify data management for diverse file system structures. This table shows how to translate different file system objects into unified key-value pairs. Those KV data are accessed via DPM-friendly vector-based access interfaces. Those interfaces accept a bunch of keys and return associated resultant value at a time. Next, we introduce the disentangled data path. It separates the data access from the data processing to leverage the vector lookup interface to saturate the aggregated DPM bandwidth and hide RDMA network latency during data read and write. The vector lookup interface is implemented via parallel pipeline Cook-Hashi lookups. The Cook-Hashi is friendly to high bandwidth memory node. For every lookup, it includes two slot probes. Each slot probe includes computational tasks and remote memory access. We overlap computational tasks with the remote memory access for pipeline and slot probe, which support this disentangled data path at index structure level. We further describe the data path design with the file path work example. Compared with the sequential coupled file path work design, we decompose the path work into a batch of de-entry lookups and remaining operations. A de-entry lookup equals a meta-object search in our data plane FS. For this de-entry lookup, the cache FS issues three lookups via one vector KV get invocation. The weak KV get computes 6 hash values for 3 keys, performs 6 parallel dependency-free hash lookups, and returns 6 lookup results. This benched de-entry lookup fully utilizes the available large bandwidth. The return value may contain false mental objects. We need to filter out correct objects, and then the remaining operations are performed on those lookup results. We conduct the experiments on a rack of 4 nodes. This table shows hardware configuration of processor, memory, storage, and network. We emulate both disaggregated PM and asymmetric PM system with those 4 nodes. Table shows even they have different hardware configurations, but those 2 systems have similar total prices. First, we measure the control plane's FS performance. Evaluation results show the log arena mechanism scales much better than log plus CAS due to small unique contention. Also, our file lineage-based dependency check perform about 200 times better than the baseline, as it effectively reduces the number of independent logs. Next, we evaluate the data plan FS performance. It shows our path walk design delivers a much more stable latency than that of sequential path walk. The data rate throughput is up to 5.7 times higher than the traditional data rate. It shows that our data rate fully utilizes the large aggregated bandwidth. We compare Ethane with Octopus, CIFAR-FS, and assess using MD-test benchmark. Results show that Ethane always performs better than other file systems. Other file systems suffer from severe performance issue. Frequent cross-node communication degrades CIFAR-FS throughput. The single-threaded MDS prevents Octopus scalability improvement. The chain replication protocol incurs excessive remote writes for assays. Those two figures show the throughput of FIO benchmarks. Ethane performs close to assess in data read and scales much better than other in data write. We find that the load imbalance issue decreases Octopus throughput. Client local NVM design improves assay performance. Finally, we use Redis and Metis applications to qualify the performance and costs of different file systems. Results suggest that Ethane achieves high throughputs and low hardware budgets. It achieves higher AOF throughputs than other file systems. As a conclusion, we reveal 3 performance and cost issues in distributed PM file system and propose a novel asymmetric NVM file system architecture. Ethane consists of 2 file system plans, and we design each of them separately to harvest hardware strengths. We evaluate the Ethane prototype and demonstrate its performance and cost advantages. This is our whole presentation. Thank you very much.